So maybe we can start slowly. These are standard, but you can look at Nakahara. I mean, for this geometry and physics, geometry and differential geometry, for that has all the standard formulas. No, that I have not, because I thought that is okay. I'll also write that in the rule. Nakara has a full chapter devoted to Cartesian forms. So you can look at it. In fact, you can also look at the classical mechanics textbook by Arnold. Even if you don't look at the classical mechanics part, the first few parts he talks about Cartesian forms. I mean, those are very, very useful actually. And a lot of walkout examples are also there. Arnold, classical mechanics, V. Arnold. Who? File? The references. Yeah, I will write it. That Google file is not shared with you guys? It has been shared. Oh, okay. The references has not been shared. I'll talk.
No,
sorry.
No. I'm telling you, I have searched yesterday. I have seen this. You go to this shortcut folder. There's a shortcut folder, and there you can find all the means. Don't go to the Google Drive. The link from where you are going to the Google Drive, that page has all the.
Okay. Let me know if it is not there, then we will again. I think it is there. Okay.
It is there.
Okay, I think I should start. Okay. May I start? Yeah. Okay, great. Okay, welcome everybody. So this is the second lecture. And what we are going to start today is what is called the symplectic structure for field theory. Field theory. So our ultimate aim is to understand for gravity, right? That's what we will also start today, okay? So what we have in a field theory, first, a set of dynamical field, okay? Set of dynamical fields, okay? And we call this set by phi, okay? So all the dynamical fields you have in your theory, okay, will be given by this set. It may carry indices if it is a, let's say, Young-Mill field or a vector field. It may have extra space-time indices as well as internal indices. But for the purpose of simplicity, I will not put indices on this, okay? And for our purpose, this set consists of course, the metric, because we want to look at a dynamical theory of gravity, particularly general relativity. So the metric is also something which you are going to vary. And possibly if there are other fields, okay? For example, if you are looking at a scalar field, a scalar vector tensor theory of gravity, okay, then you should include all possible field. If you have matter, you should include all those things, okay? But most of the time, at least for this calculation, I will work on pure gravity. So therefore, the capital T mu, I'll set it to 0. It can easily be generalized by appropriately writing down the equation and bringing out the non-zero T mu. So that's, I leave it to you to study. So this field, so now remember in the classical mechanics example, when we talked about configuration space, we talked about configuration space is the space of configurations, obviously. What it means is that each point in configuration space represent a possible generalized coordinate of the particle, how the particle is moving, right? Now here we are not working with the particle, we are working with fields, okay? So configuration space is now mean that field configurations allowed in your theory. So for example, if you are working with the scalar field theory, let's say the field configuration will be solutions of Klein-Gordon equations. Let's say your theory has equation box phi equal to 0. All possible solutions of Klein-Gordon equations forms your configuration space, right? There may be issues with the boundary condition. You may say that only certain solutions of the Klein-Gordon equation which has certain asymptotic fall off. Okay. In that case, your configuration space will be only those solutions with such asymptotic fall off. You may assume certain smoothness properties of the field. Okay, so for example, it is sometimes useful to assume some analyticity property of the metric. Okay. So with all this assumption, what you will have, is a configuration space of field configuration. This distinguishes today's lecture from the yesterday's lecture. Yesterday's lecture, the configuration space, yeah. It is disconnected. Hello. Oh, not the, sorry. Yeah. Disconnected means there could be more non-trivial structures, okay, but for the purpose of this, that we will not consider such a non-trivial structures. We'll assume some smooth properties. Okay. Now, so this configuration space we will denote is by F. Okay. So F is space of field configuration. Okay. This is important to understand that if, I mean, it could have, for example, let's say you may have to consider asymptotic properties. A good example is, for example, if you work with metric which are all asymptotically flat. Okay. So your configuration space consists of metrics which have asymptotically flat boundary condition. Okay. So this is my configuration space. Okay. Unlike the case for particle mechanics, this is something which we will work. Okay. So therefore, the variations, when we will vary, you have question? Question? Anyway, oh, sorry. So when you vary field, that variation takes place in the space of configuration. You move from one configuration to other configuration. So you assume that it is possible that there is a curve in the space of configuration from which you move from one configuration, say phi 1 to phi 2. Okay. So therefore, for example, I can write down a particular variation, delta phi would be some del phi by del lambda, where I assume there is some parameter lambda signifies the variation. So this is in the space of variations, okay? And then multiplying by some, say at lambda equal to 0 or something, okay? And then you can maybe putting one d lambda or something, okay? So I need to be careful, I'll put it delta. So variations takes place in the space of variations, the space of configurations, okay? Good. With this structure, so we will go ahead. We will consider what is called a covariant, generally covariant Lagrangian. Covariant Lagrangian. Because we are looking at a gravity theory. Of course, for practical purpose of the class, we will actually do all the computation for general relativity. But for at least indicative purpose, we'll write down the Lagrangian to be R. Okay, sorry, Lagrangian to be L, not R. Okay, I mean, what I mean is that I'll be able to write the Lagrangian L, the Lagrangian scalar, okay, is a function L of, it could depend on metric. In principle, I should have written as metric, first derivative of metric, second derivative of metric, and so on and so forth. But then equivalence principle comes into hand, because therefore we can always remove the first derivative of metric because they are not tensorial properties, and we can write down this Lagrangian as a function of metric, curvature, and covariant derivatives of curvature, call it alpha, beta, sigma, or mu, alpha, nu, beta, and possibly higher. This is the most general form of the Lagrangian you can write. And not only that, remember that there could be more fields. So let's say it can depend on psi, psi, and so on. Okay. So this is the structure of the Lagrangian with which you will be working. Okay. Clear? Now you should understand that I have written metric and then curvature. There is no mention of the first derivative of metric. I have not written this metric Lagrangian as a function of gamma, I mean the Christopher symbols. And there's a reason for it. That is because diffeomorphism invariance and equivalence principle allows me to always write the Lagrangian into this form. And if you want to know where to look for, this is listed in the reference also. Look at this paper by Wald and Iyer. Which talks about some properties of the Noether charge. That's the title of the paper. I don't remember the exact year. I think 94, maybe. I may be missing, okay? But that paper, actually, the first section will give you that if you start with a Lagrangian which contains metric, first derivative of metric, second derivative of metric, how can you always write down that Lagrangian? By suitably changing things, okay, into this form, okay? So this is what it is. This will be our starting point, okay? If it is general relativity, the Lagrangian scalar is just capital R, the Ricci scalar. If it is something like a Gauss-bonnet gravity, I will write it as R square minus 4 Arabicity, sorry, 4 Arabi plus Arabicity. If it is something more complicated, you write it, okay, whatever you want, okay? But that's the structure which we are working with. But that's only locally. Locally, gammas goes to 0, but this is a global function in space-time. So it's not that trivial. Okay. Okay. Now, of course, we don't want to use this metric notation. We will write what is called N-form Lagrangian. N-form Lagrangian. And if you remember yesterday's notation, we'll write down the N-form Lagrangian to be L equal to L into this sigma tilde. So whenever there is a form, today I put a tilde sign on it, okay? Because there are scalars also in my theory. So I'll put a tilde sign to define. What is this sigma tilde? So sigma tilde is what is called volume N form. So basically N, I should say actually D form, because D is the dimensionality of spacetime, but let's continue with N as the dimensionality of the spacetime. And how do I define this object? The definition is this object is exactly the way last class we have defined. It's an N form. So it will be some mu1, mu2, dot, mu n, d mu1. Whenever there is a form, I am putting a wedge sign, tilde sign. Okay, clear? Okay. So this is definition for an N form, okay? And for this particular volume form, this has a structure. Okay, this is not arbitrarily epsilon. My claim is that this epsilon mu1, mu2, dot, mu n is nothing but square root of minus g. And then a symbol I will introduce, mu1, mu2, dot, mu n. This is n indices Civita symbol, which is given by this formula that 0, 1, n minus 1, because I am in a Lorentzian signature, I start with 0, and this is equal to plus 1. Okay, and rest of the values are obtained by commutation. Okay, and that's the value, and other components are obtained by commutation, okay. Or rather commutation and permutation groups. Okay, so if you change any of the, it is just like epsilon ijk. Okay, in your ordinary Cartesian thing. Epsilon ijk, you write epsilon 1, 2, 3 to be plus 1. And then rest of the values you obtain by looking at the cyclic permutations. Okay, action of the permutation group on it. Okay. And if I and j, any of them are equal, you set it to 0. Why there is a square root of minus g here? Anybody? That's a density. So this square root of minus g makes the things tensors, right? So that's very important. Thanks. Okay, good. So that is why I have this square root of minus g. Good. Now what we should do is that, let's see if I put this guy here, what will happen? Okay. Let's do that. Okay. So what I will do is, let me do it here. Okay. So I will first look at the tilde equal to L n form. And what is this object I should write? I write it as L as it is, 1 by n factorial. This object comes, this object is this, square root of minus g, mu1, mu2, mu_n. Let it be like that. Now I have this wedge product. Remember that this wedge product is also completely antisymmetric. Okay, so therefore I should be able to write, let me write it here, that d mu1 wedge d mu2 wedge wedge d mu_n. This is nothing but a minus sign. This is simple product of all these objects x1, x2, x3, mu1 with this antisymmetric tensor built in. Now you should ask me, what is the origin of this minus sign? Anybody? Yes, that is because this is, I'm writing it up. If you make it 0, 1, 2, 3, 4 up to n minus 1, this should give you minus 1. And so therefore, this minus and that minus give me plus 1. Okay, that's all. Okay, so therefore there is a minus sign because I'm using signature, Lorentzian signature, minus plus 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 plus. Okay, that's the signature I will be following. Okay. Good. Now let's put it there with a minus sign, and then I will have mu1, mu2, mu_n. Okay. Now let's see what will happen. I will have minus L by n factorial square root of minus g dnx. And then what is this object? If I contract, minus n factorial actually, because of the contraction, figure it out. Okay. So this object and this object, this contraction will result into minus n factorial. Best way to check it, you express this box tensors in the form of deltas in 2 or 3 dimensions. Okay, 2 or 3 deltas. Okay, like in 4 dimension or 5 dimension, and try to see whether this normalization works. Okay, and therefore what you have, this is nothing but L square root of minus g. So it is clear what we have worked with this object is exactly what we have written if you are using the metric notation. Okay. So is that clear? So this is Lagrangian multiplied by the dV, the invariant volume. Is the notation clear? This notation, but we will stick to this notation. Okay. Okay, should I go ahead? Good. Okay. So with this notation, my theory is then given by a Lagrangian n form, which is L epsilon. Again, note that this is a top form. Okay, because I am working with n dimension, I have n dimensional Lagrangian n form. So there is no such thing like n plus 1 form. Okay, as Jahanur has proven yesterday, that this is what it is. If you go ahead in the further ladder by operating exterior derivative, you will get 0. Okay, clear? Yeah. G negative mean? Oh, that's that is because physics has told me I have to work with a pseudo-Riemannian manifold. This is the volume of the entire space-time. Okay, square root of minus g. So think of it that I have a minus plus 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 signature. So therefore, if I multiply it, take the determinant of the metric, it is guaranteed it will be negative. That minus sign makes it positive. Why the determinant turns out to be negative? Because I'm working with a minus plus 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 signature, and it is, why in the minus plus plus signature? Because physics has told me I have to work with a pseudo-Riemannian manifold. The special relativity tells us they have to work, that's all. But you are right. For example, if I write a surface integral, for example, the surfaces, even if I'm working with a pseudo-Riemannian manifold, surfaces can be both space-like as well as time-like. There I have to take care of the sign of square root of minus g. Here, the space-time is pseudo-Riemannian given to you. Okay, we will carry on. Is that okay?
Same will be the case even if you consider plus minus.
Yeah. Of course, it has to be the case, but I am sticking to physics is independent of the signature. But I am sticking to minus plus plus signature. You could still take the plus minus minus, plus minus minus signature. If you multiply it, you can see plus minus minus minus. You can figure it out the determinant. Determinant will still be negative. No, because if you take 1 plus 4, then what are you saying? No. Yeah, but I know no, this G has a definite sign. It's not that G is changing its sign. This G has a definite sign. This is general relativity, right? It's not that it will change its signature. The signature is fixed. So therefore, G is always negative. So therefore, but suppose you go to a submanifold. That submanifold could be space-like as well as time-like. So if you take the determinant, you should put mod. Because H, the submanifold determinant of the submanifold induced metric, could be both negative and positive, depending on whether you're looking at time-like surfaces or space-like. Yeah? That you figure it out, why there is a minus sign. Why I'm telling you is, the normalization of it would require, look at this. Yeah, this is normalized to +1. So if you take everything up, it will be normalized to -1. That is the reason for this minus sign. Yeah. Any other question? Yeah.
Actually, instead of 1 plus 3, you take 1 plus 4.
Yeah.
One time in that one. Then G can be positive.
But then this G is the, this G is the metric of what? Then?
Yeah, it is the 4 space axis.
But that is not what I'm looking for. This is the volume of the space-time.
Oh, okay.
This is Lagrangian is the Lagrangian of the space-time. This is like in general relativity, simple general relativity. R square root of minus G d4x in 4 dimension. Here, I'm writing it R square root of minus G dnx. Okay. Clear? That's all. Okay? Should I go ahead? Okay. Now let's go to more on this. Okay? So, what we have is my Lagrangian, which is L tilde. Now, what I want to do is that I want to vary this Lagrangian, obtains my equation of motion. Okay. What do I vary? I vary phi's, the field configurations. Okay. In the space of configurations, I vary the field configuration infinitesimally and look at how Lagrangian is changing under that field configuration variation. Okay. So I call that to be delta L tilde. Okay. So this delta lives in the space of variations. Again, remember it. Okay. And then what is the general structure? You already know that the general structure is always of this. This part will give you equation of motion. And the other part, there is a surface term, which is a total derivative, theta. Okay. Okay. And what is this theta? In general, it depends on the field as well as the variation of the field. Clear? Is that part clear? Everybody? Okay. So if I vary the Lagrangian, I get, this is the equation of motion. You take any ordinary Lagrangian, half m q dot square, okay? If you vary it, you get the equation of motion, q double dot dq plus a surface term. And that surface term, I've written it into this notation. Okay? Okay. I want to show that this is exactly a surface term. We will see that it can be written as a divergence, okay? But let's, for the time being, let's go ahead with this, okay? So the equation of motion, this is a pure theory. I mean, this only this Lagrangian, there is no matter into it, okay? So what will be the equation of motion? Sorry, equation of motion. That will be E phi equal to 0. If there is matter, instead of 0, the matter will contribute, okay? Clear? So for example, if this is Einstein-Hilbert Lagrangian, you will get G mu equal to 0, capital G mu equal to 0. Okay, good. Now, the boundary term boundary total derivative term is this theta bar, which depends on phi and delta phi. Okay. Clear? Now, from the space-time point of view, everything is a scalar, right? I'm just starting with a scalar, I'm varying it, all the space-time indices will be contracted out. But in the space of variations, this object, important to understand, is actually a n-1 form. Is that clear that this is n-1 form? This is starting with the n form, this d acting on it, and it takes delta phi as an input, which is like a vectors in the and on the space of variation. So therefore, this is clear. This is the n-1 form. Okay. So this is analogous to in classical mechanics. How do we define that p dq form? Okay. Clear? Again, let me emphasize here the variation in the space of variation, that f. Okay. Good. Let's go ahead. Now, obviously, this is not uniquely defined. Okay. I can still add, for example, with this theta, something so that the structure will not change. And that is because of the fact, what again we have proved in the yesterday's class, that d square is equal to 0. Okay. So let's look at it. What are the ambiguities? Okay. Ambiguities in boundary term. These ambiguities are very, very important ultimately in the construction of the Wald entropy. Okay, these ambiguities are important because we will see in the construction of the first law, ultimately these ambiguities will affect the what is called the noether charge and the noether current. But thankfully, because of some technical assumption related to the structure of black hole spacetime, ultimately these ambiguities will not affect the black hole entropy. For example, from the first law for general relativity, we will show that area is the entropy. Kappa by 2 pi into delta area will be equal to the, say, delta m, if we're only looking at static cases, okay? In that case, this inside delta, what will come is the area by 4. And we will show, although the noether charges and noether currents depends on this ambiguity, they will change if I add new terms in the theta. But the black hole entropy obtained from the first law will be independent of the ambiguity. Otherwise, we'll be in trouble, right? I mean, if everything depends on if the things are ambiguous. This is like, for example, the ambiguity in the vector potential in electrodynamics. They're ambiguous after addition of the gauge transformations, right? But the physical quantities, electric and magnetic field, does not depend on those ambiguities. The same thing will happen. So what are the ambiguities first? For example, with this guy, I can say, I can take theta bar and change to, sorry, theta tilde. I can add another new form. And dy is again a function of phi and delta phi. Okay. Is that clear? Now it is clear, you show that because if I put it here, this d will act on here. And d square is identically 0. Okay, so this ambiguity, so this and this will result into same structure of the variation of the boundary term. So therefore, I can work with this theta, I can work with this theta also. Is that clear? Okay. What kind of form y bar is? Is it n minus what? N minus 2. Good. Because I am taking a d. Okay. Good. No, I'm not saying concept charges will not be physical. No, careful, Shanti. The measurable quantities are not just noether charges. These are noether charges integrated over surfaces. Okay. Those quantities will be independent of any such ambiguities. Okay. But the Q, that will depend on the ambiguity. But let me put the horse behind the cart. Just give you, since you have asked. This idea that the entropy is Wald entropy is independent of ambiguity requires certain technical assumption. One of the technical assumption is that you have to have a stationary black hole horizon, okay, with certain structure called bifurcation surface, which today in the tutorial, Shubhayu will discuss, okay? So if you don't have such structure, you cannot prove that Wald's construction is independent of the these ambiguities. This has been proven by a paper by Jacobson and Kang. Okay, this paper, I think it's called On Black Hole Entropy. I don't remember the exact date, 94, 95 maybe, where they shows that if you make this assumption that you are given a stationary killing horizon with a bifurcation surface, then none of these ambiguities matter. But if you do not have, for example, if you have a perturbing black hole, then ambiguities matter. And in fact, it is matter very, very important because you can use these ambiguities to choose a particular entropy which will satisfy the second law. Okay. So this ambiguities plays a very important role, not in the first law, but in the second law. That's like talking about the fifth lecture today. This is because they're ambiguous. Which one is theta and which one is not? You can call it theta, you can call it this as theta. That's why it is ambiguity. So you cannot say this, what is your theta? If I tell you from this variation, give me theta. You can quote this theta, you can quote this theta. So the value of the theta is ambiguous up to addition of this form. Okay, closed form. Clear? Let's go ahead. But this is not the only ambiguity, okay? There is also another ambiguity. What is another ambiguity? Look at this Lagrangian. Okay. We all know that I can add a total derivative with the Lagrangian. Equation of motion will not change, right? Total derivative, which is a function of phi's. Okay, agreed? So that will, but the total derivative, once you add to the Lagrangian, it will add here also. Okay, so there is a further ambiguity in the definition of the theta, starting from the Lagrangian ambiguity. Okay, so for example, I can take L tilde equal to L plus D mu tilde, UM, equation of motion, remains invariant. Okay. This is, we all know, okay? But in that case, what will happen to the theta? Let's calculate it. That's easy to calculate. Equation of motion is identical, but if you put it in theta, then but this will change theta, this will change theta to theta tilde prime, which is theta plus delta mu. Can you convince yourself? See what I did, d and delta I interchange, and I can always do that. Okay. Is that clear, everybody? Oh, tilde and mu, thank you. Yeah, yeah, sorry. Yeah, let me be consistent. Why I can exchange d and tilde? Which space d acts and which space delta acts? You convince yourself that I can actually exchange. So therefore, if I put here d mu, I will have delta d mu. I exchange d and delta, and then this theta bar changes to this. There is this ambiguity also. Okay? Good. So therefore, unlike the ordinary classical mechanics case, this theta form will have ambiguities, of course, that is there in classical mechanics, and it's a function of field configuration and variation of the field configuration. Okay, good. With this, let me take the example of Einstein-Hilbert-Lagrangian and just to see how the things look like, because with the example, things will be much more clearer, okay? So let's see Einstein. Hilbert Lagrangian. I hope all of you know the story that how Hilbert got the Lagrangian, but Einstein got the field equations. Okay, that's a very interesting story. If you're interested in interesting parts of history of science, do look at Hilbert's role in general relativity. It's a remarkable thing. Okay, good. So how do I write down the Lagrangian? So action is 1 by 16 pi j. This is general relativity, so the action is R with volume form on the manifold. This is my n-dimensional manifold, okay? And then I have also a surface term that I may not write, okay? You require a Hawking-Gilbert surface term to get the correct variation, but for the time being, we'll work on the bulk Lagrangian, okay? Once I have this object, let's calculate the variation of the bulk Lagrangian, okay? So what do I vary? There is only one field. What is that field? Metric, not matter, metric, right? Metric is the only field. There is no other field, dynamical field in this theory. We have switched off all the fields. So let's vary metric. So if I vary metric, so what I will do is that I will write R as R mu nu, G mu nu, and vary the up component of the metric, the contravariant metric. Okay, please, if you have not done so, derive the Einstein's equation varying the covariant part, the actual G mu nu down, because it is instructive, okay? You will see, learn something, okay? There will be an extra term which will come, which is important, okay? Because none of the textbook actually do it. I think Paddy's book does it, okay? You look, at least he mentioned it, I'm sure. That you could have written it like G mu nu, right? And work with this as your field. But all the textbook takes this because the equations become simpler, okay? But please do it yourself once, okay? Good. What is this volume form? This is in the manifold, and by our earlier definition, we'll write it. Again, this is pseudo-Riemannian, 1 by n factorial. Mu1, which mu2, which dx. Okay, n-dimensional volume form. Okay, and you know that this will reduce to R square root of minus z d4x if I want to write it in ordinary metric notation. Okay, that we have convinced ourselves. So let's vary this action and see what is the variation of this action will look like. Okay, so the variation of this action will be delta action. 1 by 16 pi j remains as it is. I'm not going to vary G. This is manifold, okay. First variation will come in the square root of G manifold variation, okay. And we all know the answer. I will write it because these are standard textbook stuff with a minus sign. And but then the actual interesting stuff, again, variation of a manifold. I'll have R mu nu delta G mu nu plus G mu nu delta R mu nu. Agreed? There is this structure already there here. Okay, it is already put here. But it is, you mentioned it rightly. What I have used is delta of square root of minus G is equal to half minus G mu nu delta of G mu nu square root of minus. Okay. If I use all down, I would have got the same thing without a minus sign. Okay. Agreed? Okay. This is standard stuff. Let's go ahead. Okay. Good. So once I have the variation, what should I write then? Okay, let me go ahead. Let me work it out, this structure. Okay. So therefore, variation of the action is integral. What I do is that I write 16 pi g here. Then I don't have to write it many of the time. Equal to, I have manifold, and look at this. This depends delta G mu nu, and here there is a delta G mu nu. Okay. So therefore, I will have R mu nu minus half R G, sorry, half R G mu nu. Is it clear how the R came? Everybody? Is it clear? I think, did I miss anything? No. R mu nu? No, there is a R. Sorry, yes, of course. I missed this capital R. Sorry, there is a R. Look, this is R square root of minus G. R variation of the square root of minus G. Okay? So there is this R. Okay, let me write it carefully then. R G mu nu. Okay. And what do I have? Delta G mu nu. This is this term and this term. Okay? This term. But I also have a extra term, which is integral m, 16 pi g I have taken, m, and then I have g mu nu, delta r mu nu. Okay? Compare with this structure. Okay. I already got the E phi, delta phi part. But this part is yet to come. Okay. I have to show that this is actually a total derivative. Okay. And then find the theta form out of it. Okay. Let's go ahead and do it. Good. Yes, there's also an option. Good. Thank you. Okay. Okay. So let us understand the structure of this term. Okay. So this is G mu nu delta R mu. Sorry. Delta R. So the best way to calculate this thing, see, R mu nu contains gamma gamma and del gamma, right? You go to a local inertial frame so that you can throw away those gammas, and then you calculate the variation in a local inertial frame. And then whenever you have ordinary derivative, close your eyes, make it partial derivative. Sorry, close your eyes, make it covariant derivative, right? That's the easiest way to do that. Then you have a generally covariant expression. That's the trick we will do. And if you do that, you can show this is not, I'm going to derive, okay? You have to derive yourself, okay? First of all, I may do mistakes, and I don't want to reveal that. Alpha mu nu, okay. Sorry, alpha. Delta. I'm doing mistakes already. Yeah. Okay. Is it expected that will happen? Because look, what I have done is that this object is gamma gamma del gamma del gamma. It contains derivative of gamma as well as the gammas. I go to a local inertial frame, set the gamma set to 0, but not the derivative of gammas. I vary it. I change every ordinary derivative to covariant derivative. This is the structure you will get. This is a covariant structure. Okay. This is important. You just go, it will take few lines to derive. Okay. Once you have it, let's play with it. First of all, what we'll do is that we'll want to, so what is the aim? To show that this is a total derivative, right? That's the aim. So in ordinary metric language, we will convert into what is called a total divergence, right? And then we figure it out, what is this theta form for us, for general relativity. Let's go ahead and do it. So let's take this guy out, because we want to prove it to be a total divergence, okay? And this will go inside, because this is covariant derivative. I will have G mu nu delta gamma alpha mu nu minus G alpha beta delta gamma mu beta. Convince yourself they are same stuff, okay? Just because if you take this guy here, it will hit here, and you just change the naming of the indices, you'll get back the same thing. Okay. Good. Now, what I have to do, I have to calculate this object. Okay. Okay. So let me write down the formula. Again, you should be able to derive this alpha. Show that this is nothing but half G alpha beta minus del beta G mu nu plus del mu beta nu nu g okay. Again, the covariant derivative is important. Note the covariant derivative is acting on the variation of the metric, not on metric. Otherwise, you would have 0, 0. Okay, clear? I will not go there. Okay. Okay. So with this structure, let me not, so this will remain as it is. I will not remove these lines. Okay, this part is important. Let's go there. And calculate. Okay. You can show ultimately your G mu nu delta R mu nu. This object will turn out to be delta lambda, delta alpha, sorry, grad alpha, G alpha beta. Sorry, beta mu. Let me just be a little consistent. Alpha. Okay, we have almost achieved our game because we have proven that this quantity is actually a total derivative. Okay, but we have to go to the form notation. Okay. So therefore, we define this object, this entire object, as theta alpha. You clearly see the only index there which is not contracted is alpha. So del alpha, L alpha, theta alpha is the form. And remember that there is a 16 pi g that side. If you go, I don't want to walk, it's too far. Okay, which I set it into the action side and I bring it down. 16 pi g. Okay, I will call it G alpha beta del mu delta G beta mu minus E mu nu. Okay, remember this. This is important equation. Okay. Okay. So what is the structure we got from the variation of the Einstein-Hilbert-Lagrangian? Okay, let's write down the structure. Delta A equal to integral, okay, E mu nu delta G mu nu with the volume forms set in. Plus we got another structure, delta M del alpha theta alpha, okay, and then okay, but I have to write in a form notation. Okay, so let's go ahead and do it. So this is perfectly okay. This is E phi delta phi. This I have to structure and write it as d phi, okay, or d theta. Okay, so let's go ahead and do it. Let me remove this part. Quite slow. Capital G mu nu. Yeah, I'm just writing it as E mu nu because okay, since it is Einstein's theory, let me call it G mu nu. You're right. Okay, it's better to call it G mu nu. Okay, good. So how do I define this object theta? So note that what do we have? Let's go ahead there. Here we have this term. Okay. So we have to find what is the form theta bar such that d of theta bar is related to del mu del alpha theta alpha, right? Of that vector. So let's go ahead. So first I will write the answer and then I'll convince you. So my claim is that if I define the form to be a theta alpha, which is this object, into square root of minus g 1 by n minus 1 factorial with the index alpha mu1 mu2 dot 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 mu n dx mu1 which dx mu2 which dx. My claim is that then this part, where is that? This part will be equal to d of phi tilde. Okay. So we have to prove it. Okay. Note that this is exactly an n-1 form because this index is contracted out. Okay. Okay. Clear? Okay. Should I go ahead? Let's see. Okay. What is d of phi tilde? Theta tilde. Let's see. What is this object? Let's use the definition of what discussed by Jahanud last class. We will take d of mu1. This is the index. Square root of minus g. Theta alpha. This object is 1 by n minus 1 factorial. Alpha mu1 mu n. Let's do this. Okay. And then I have d of x. Yeah, yes. Oh, this, you have to be careful. I will look at this. That's a very good question. This is the form in the space of variations. So it takes phi and delta phi. Okay. In the tutorial class, I mean, it is advanced form in the full spectrum, right? N form, yeah. So Lagrangian is the N form. So this is D of the N form. So if N is 4, then this is a 3 form. Even in spacetime, because D is acting on spacetime. Okay? Yeah, thanks. It's a configure phase, it's a 1 form. Because it takes only delta phi as the input. Okay. Is that so? No, it should, sorry. You are right. It should start with mu2. Yeah. Okay. No, that's fine, right? That is fine. Let it be mu1. But it started, did I wrote it wrong? I think it should be started. Okay, fine. Sorry, yeah, my index problem. Okay, let's go ahead. Okay, what did I write? So this is mu2, mu3, mu2, which d of mu2, and I'm one second. There is, so this is mu1, so there is a mu1 now, and then x mu2 dot which x mu1. Correct. Thanks. Okay. Now it is perfect. Okay. Because I am going to the higher form, I take del, I adjusted a d mu1, and rest of the things are there. Okay. Let's go ahead and check it. These are just objects are go ahead, and then what I'll actually have is del of mu1 square root of minus g theta alpha into 1 by n minus 1 factorial. Then I have alpha mu2 mu3 mu n, and then I will have this object is minus 1 dnx mu1 mu2 dot mu1. Okay. Exactly the way last time we have defined the normalization. Okay. Now you can clearly see what will happen is this alpha is contracted here. Here there is n minus 1 indices. There are this n minus 1 indices, and therefore you will have this structure nothing but del of mu1 square root of minus g theta alpha 1 by n minus 1 factorial, and then you will have minus. See, in this normalization, you will get 1 minus sign. Here there is a 1 minus sign, that becomes plus. You will have n minus 1 factorial and a delta mu1. Okay. And therefore, what you get is del alpha is last, I hope it is visible, square root of minus g. Okay. Clear? Okay? Is it clear? There is not, because this alpha is contracted here. No, but you take one of the deltas out, you write this Lewis-Civita symbol is a product of one delta mu1 alpha into other lower Lewis-Civita symbol. Each will have, now you take the contraction with that, and that will give you a delta alpha mu1 plus an n-1 factorial into a minus sign. You have to, you can, the best way you break it down in the smaller deltas, okay? Good. Now, this is nothing but, should be able to convince yourself, square root of minus g, grad alpha, theta alpha, dnx. Sorry, there is a dnx which I have not written, sorry. This object. Okay? Clear? So what I have here is nothing but integral manifold d theta tilde epsilon. Okay? Okay. Now let us compare with our structure here. We have achieved writing down the variation of the general relativistic Lagrangian into this form. Let me write it carefully because this is going to be an important result. This is we are going to use. General relativity. Okay. What do I get in general relativity? My action is 1 by 16 pi g square root of r manifold tilde over the manifold. Okay. I write down the variation of the action 1 by 16 pi g and e, sorry. Let me use the notation e because I will anyway generalize it to other Lagrangian. So for the time being, the Einstein tensor, I call it capital E. Huh? I hope that's not confusion. Because of obvious reason, here I have used E. So E is the equation of motion for any general. Delta G mu nu, and then I have 1 by 16 or okay. This I'll put it into E, okay, into M D phi tilde, okay, and let's see, okay, and here there is a volume form. Here also, let's put, let's keep it that, okay. I don't need the volume form because this is already defined in the, it is already included here. Okay, okay, okay. Huh? Epsilon tilde where? Yeah, okay. Is it required? I think it's, I have already included it, right? One second, it's different. So this object, look, this object is, this entire thing is actually d theta. So this entire thing is square root of minus d dnx. So within its definition, epsilon tilde is included. Okay. So we'll just call it, where am I? Here. Okay. Now let's write it, what is theta tilde? This is again, let me write theta alpha square root of minus g 1 by n minus 1 factorial. Again, mu1, mu2, mu n, okay, and then I have dx mu1, which dx mu2, which dx. Okay, this is one, and then again write down what is theta alpha, okay, because this is going to be important. It includes the 1 by 16 pi j. G alpha beta del mu delta G beta mu, obviously beta mu minus G mu nu, and I will have del alpha delta G. Okay, clear? So if even if you forget everything, this is the chart which is important. Okay. Note that this is equation of motion. Note that this theta form depends on metric as well as the variation, first derivative of the variation of the metric. Okay. Okay. So this structure is going to be very important when we are going to derive the Wald drop. Okay. Good. Now, let us come back to the general structure here. Okay. Let me. Yeah. Where? Aha, sorry. So indices are giving me pain. How did I write it here? So mu2, mu3. Thanks. Sorry, my mistake. Mu2. Okay, thanks. My mistake. Yeah, thanks for pointing it out. Okay, because it's important. Okay. Capital E is Einstein tensor, but let me keep it capital E because in general, this is the equation of motion. For GR, it is nothing. Okay, let me write it. I think you're right. E mu nu, R mu nu. I hope Einstein forgive me. Okay, calling it E mu. Clear? Good. Good. Okay, now I will do something more. Okay, let's go ahead and do something more. Okay. Now, what do I did in the classical mechanics? I have defined the theta form and then I have defined omega by taking a d on the thetas. Okay? Okay. And then I called omega to be the symplectic current, and I relate it with the using the what is called the I derivative, the interior derivative. I have related it with the Hamiltonian. Okay. We will do something of that sort. Okay. But so main idea is that you take this theta, you find something out of the thetas, which is some structure like d of theta. Okay. And then which is actually a closed form. Right? That's what you have to derive. Because remember, d omega was 0, even in the classical mechanics. What first thing to notice is that these objects are forms in the space of variation. Okay. So omega will also be a form in the space of variation. So therefore, instead of d here, I have to take deltas. Okay. So let me go ahead and first write down the formula. Okay. And I will not spend much of it here to justify why this is. It will be better if we use the tutorial sessions to show that this is omega is actually related to the classical mechanics definition of d theta, and also we will show that this is a closed form. Okay, and that is related to what is called the second variation of the Lagrangian. See, you notice something. Even in classical mechanics, when we wrote theta and omega, theta came from the first variation of the metric. Okay, but when I take omega, small omega, that came from there is another d acting on it. Okay, so that is related to the second variation of the metric, of the Lagrangian. Okay, same thing will happen here, and that allows me to define what is called pre-symplectic current. The word pre, let it be. I'll try to explain why I'm using the word pre. Then I'll just remove the word pre from the board. Okay, but it is important. Okay, pre-symplectic current. Okay, so yeah, make it delta G. This is beta. Let me check. Alpha is there. This mu. This should be beta. Thanks. You are master of index. Sorry. Yeah. Okay. So the definition is that in the space of variation, I can consider different directions of variation. Okay. So let me consider two variations. First delta 1 and delta 2. Okay. So consider two variations. So remember, what does the variation means? I have a configuration of fields. I can move from one configuration. Each point is a one configuration of field. In modulo the asymptotic conditions, smoothness conditions, and whatever, I move from one point to other point. I can move in different direction. Let me move a direction delta 1 first, and then move a direction delta 2 first. Delta 1 and delta 2. Okay. I could have put in delta 1 phi and delta 2 phi, but it doesn't matter, same thing. Okay. The only thing what I'll assume is that delta 1, delta 2 equal to delta 2, delta 1. Okay. That means if I move in delta 1 direction and then go to delta 2 direction, or if I move in delta 2 direction and then go to delta 1 variation, I arrive at the same point of the configuration space. Okay. These variations are chosen like that. Okay. If I do that, then we can define a new object called the pre-symplectic current, which is also a function of phi, but now it depends on two variations. Okay. And it is given with this formula, delta 1 acting on one of the theta. So each variation, I can vary the Lagrangian into like this. Sorry, here. Okay, each variation. So for delta 1 variation, when this is delta 1, I will have 1 theta, where this is delta equal to delta 1. Similarly, if I vary delta 2 variation, I will have another theta which is for delta equal to delta 2. Agreed? Okay. So therefore, I write it as theta tilde, which is a function of phi delta 2 phi. Remember, delta 1 acting on theta, which depends on phi, and delta 2 phi. Let me anticipatize it. Delta 2 acting on theta, phi, and delta. You have to believe me that this is a form which is closed. Okay. Okay. That means one should be able to show this form can also be written as a omega alpha in the basis, and divergence of omega alpha is actually 0. That comes from the fact is basically this operator acting on the Lagrangian gives you the same thing. But this I will not prove in the class because I then have to go to the index gymnastic, which I'm not very good at. Okay, already you have seen the example, so I'll give it into more capable hands, like Jahana will do it. Okay. So this object is a very, very central object in our calculation. And we have to show, of course, we will not show, we will state that this plays the role of what we have called omega, small omega, in the ordinary particle mechanics. Okay. But remember, this is far more subtle. It involves two variations, delta 1 and delta 2. Okay. And that is because without that, you cannot prove that this is a closed form. Okay. So in field theory, this structure is important. And it will generate the Hamiltonian flow, which will prove in the tutorial that this is actually related to the Hamiltonian interior derivative along the direction, sorry, the I derivative along the direction of the Hamiltonian flow. Okay. So this will be the symplectic form. Now the question is, why the hell I put this pre word? Okay. That is because, remember that I'll not remove this part, I'll keep this part. Yeah. It is of, let's wait for the tutorial, you will see the structure, okay? I'll not remove this part. And then, I can remove this part. This is not important. Okay. Where was I? Here. Okay. So why the hell I use the word pre here? Okay. That is because I have not told you something important. Let's go to even in classical mechanics. Okay. Classical mechanics, like of the point particle. Okay. So there what we had a theta, which is pi dqi, and we have omega, which is of d theta, okay, and d square omega is equal to 0. Okay. Okay. And we have also wrote down, given a Hamiltonian vector field chi, we have shown in the tutorial that this is 0. Okay. Why it is 0? Because of the Cartan formula. Okay. Last time we have shown. Let me write it down again, that d of interior derivative of chi plus interior derivative of d omega. Okay. Now suppose I don't give you the Hamiltonian vector field, I give you a vector field in the phase space. Okay. Yeah. Where? This is this side? D omega equal to 0. Sorry. What I mean to say is like d square theta equal to 0. So d omega equal to 0. Sorry. Okay. 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 So suppose I give you a vector field. Okay. Which is not a Hamiltonian vector field. Okay. But I tell you that this is true. Suppose this is now given to me. Given. But I have not told you this is a Hamiltonian vector field. Okay. Okay. This is true for every form. Okay. Okay. Now what can I obtain from this? See, this phi or omega by definition is d theta. So therefore this object will automatically go to 0. Okay. So suppose this is still given to you. Okay. So this object is automatically go to 0. So you have a structure d of I chi omega equal to 0. Okay. But there is nothing like Hamiltonian or anything is given to you. So therefore you cannot write I chi omega equal to dh. This is not yet given to you. Okay. This is for an arbitrary vector field, but in the phase space. If this happens, you would have called I chi omega to be a what kind of form? It's a closed form. It is not exact, okay? It's a closed form. Okay. So vector field for which this object is a closed form, that means d of this is 0, we call it a symplectic vector field. This is definition. But modulo, a very, very important fact, this omega is a non-degenerate form. What it means is that if you look at the matrix has non-zero determinant. Okay. Or in other words, if this object I chi omega is 0, it is only possible if chi is 0. Okay. There is no vector field along the direction I chi omega is 0. Okay. This is called a non-degenerate form. So any given a non-degenerate form omega, if this is in closed form, we call this chi to be a symplectic vector field. You can show, and it is obvious from this example, every Hamiltonian vector field is symplectic. But the other way around, it's not true. A symplectic vector field need not be Hamiltonian. Find an example. Can you obtain an example? Not now, maybe later. A symplectic vector field, which is symplectic but not Hamiltonian. Okay. It's easy to find. Even on sphere, you'll find it. Okay. Good. Now, the crucial assumption there is that omega is non-degenerate. Okay. That assumption is there. But what it turns out, the way we have defined this object in field theory, a priori, there is no guarantee that it will be non-degenerate. And that is because there may be local symmetries in the field theory, particularly gauge redundancy. What does I mean by gauge redundancy? Gauge redundancy means there could be directions in the phase space which are completely fake. You may move along that direction by interior vector field, but omega will not change. Okay. So then omega form will be a degenerate form. What is a gauge symmetry? These are redundancy, right? Field configuration related by gauge transformations represent the same physical state. Like if I have an electromagnetic field configuration given by vector potential A and a vector potential A plus the gauge transformation, they represent the same physical state E and B. Okay. If there are local symmetries in your theory, and in gravity there is the diffeomorphism symmetry, you can think of non-abelian gauge theories where there are local symmetries as well as internal symmetries, and local symmetries are there, gauge symmetries. In that case, this object need not be guaranteed to be non-degenerate. Okay. So then what you have to do, you have to somehow gauge out, coset out the gauge transformation. That means you have to do certain extra mathematical procedure to fix the gauge degrees of freedom, because gauge degrees of freedom are not physical degrees of freedom. You have to somehow switch off the gauge degrees of freedom and only work with the physical degrees of freedom. Okay. A good example would be, let's say if you have a mu which has 4 components, you can choose a Lorentz gauge. Further, you can choose another gauge subsidiary condition, and you are left with only 2 physical degrees of freedom. Like an electromagnetic field has only 2 physical degrees of freedom. Okay. Similarly, that is a procedure has to be done here. Otherwise, this is not going to be actual symplectic current. Okay. That is why I use the word pre. Okay. Of course, I'm not going to do that because it's just long and mathematically a little bit non-trivial. But let me point out the example, the correct reference, the best, one of the best reference you can look at it is by Lee and Wald. Lee and Wald. This is Journal of Physics. Journals of Math Physics. Math Physics. And this is in 1990. I think 1990. I maybe just give Lee and Wald. It's called Local Symmetries and Constraints in Local Field Theories or something like that. Okay. This is the paper which actually tells you how do you actually construct this from pre-symplectic form to symplectic form. Okay. But for our purpose, we will only work with this. We will assume that all the subtleties can be taken care of. Okay. By taking appropriate coset with the gauge groups or not. If you're familiar with this statement, it is fine. If you're not familiar, it's perfectly fine. You assume that there is some mathematical procedure by which we will be able to switch off the gauge degrees of freedom and only extract the physical degrees of freedom. And we'll work with this. Okay. And then, once we have it, we have our omega tilde equal to delta 1, theta 2. I will not write theta 2, I will write full thing. Phi, delta 2 phi minus delta 2 phi, delta 1 phi. Sometimes I will call it delta 1 phi theta 2 minus delta 2 theta 1, just to shorthand notation. What I mean by theta 1 is I'm considering variation in the direction of phi 1. Okay, is that part clear? Good. Now we have already theta bar. Okay, so you have already theta. Okay, if I have theta, the question is, how do I construct omega? Okay, we have all the definitions there. In principle, we just look at this definition of where is my theta? Theta tilde, okay. We should be able to construct the omega. Okay, that calculation is longer and contains more indices, so it will be prone to more mistakes. So I will not do it. Okay, but I will give you the final result. Okay. So where should I write? Maybe I'll write it here. So I will define, so omega tilde, I will call it, what I do, I use this structure. Okay. And I put it into this variation. Okay. Okay. You clearly see this is like, look at this theta. This contains, where is my theta? There's so many things. Yeah. Delta. If I take another delta, it will be the second variation, as I pointed it out. Okay. So, where am I? You can write it as delta 1 square root of minus g theta alpha 2. I hope this notation will be clear. Theta 2 square root of minus g 1. And then these structures will come, these objects, okay? And I will write it 1 by n minus 1 factorial, okay? Alpha mu 1, sorry, again mu 2, mu 3 dot 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 mu n dx mu 2 wedge dx mu 3 dot 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 wedge dot 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 dx. Okay? And I call this object to be obvious notation omega alpha. Okay? So what you have to do, you have to be brave enough, take that theta alpha, put it there. There will be two terms. One will be delta acting on variation of square root of minus g, which we know how to write. And then there will be another term, delta acting on theta 2. So that means you have to take another variation here. Okay. That variation will act on here as well as here. You fully write down everything, whatever you want, and you will have a huge number of terms. There will be a lot of symmetries, and work it out, and you will get this following structure. Let me remove this. What is the time we got? Okay, 10 minutes. This is definitely not derivable in 10 minutes, that's for sure. But I suggest at least once. Okay, I have also done once or twice. Okay, not more than that. Okay, so at least once you should do it once in your hand. In fact, let me see whether we can do it for a general Lagrangian, at least symbolically the theta and the omegas. Let's see whether we can work it out in the tutorial, but just too long and there's not much illuminating things other than the tense. But anyway, let me write it down. So the structure we will get is this. Is again 1 by 16 pi g will come, and I'll write down an object which I'll define later, alpha mu nu beta rho sigma. I'll define this object, what it is. Then it is expected, this what kind of structure we expect? But the structure should be clear to you, that what kind of structure. Delta g into variation of delta g. Then there will be another structure, g grad of delta squared g. Okay? I mean, delta square means delta 1 into delta 2 or delta 2 and delta 1. That structure should be clear. So therefore, we will write that structure. Delta 2 g mu nu beta delta 1 g sigma. I hope all the indices have contracted. Yes. Minus delta 1. It has to be antisymmetric in delta 1 and delta 2. G mu nu. Then this is same thing, but this is delta 2. G sigma. Okay. Note that this contains, the structure should be clear. Okay. It's the product of two variation. Okay. And what about this object? Okay, this object is a huge object. Okay, let me try to write this. G alpha mu beta rho sigma is equal to, okay, G mu, sorry, alpha rho G beta nu G mu sigma minus So some terms have half and some terms don't have half. So you have to be a little careful. Mu rho, mu sigma minus half G, sorry, alpha mu, let me root it, G beta nu, G rho sigma. It's not very illuminating, except you may figure it out what are the symmetries of this object. G alpha rho, G beta sigma, okay? And the last term, half G mu nu, G alpha beta, G rho sigma. Let me count 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Huh? Where? One index? No, why? One second. There will be 1, 2, 3, 4, 5, 6. What did I wrote? G, one second. Mu nu. Here did I miss anything? P. Okay. So mu. अरे ठीक है, एक new है. Mu new. Okay. That new was there. It was invisible. Okay. Okay. So there is something called law of requirement in teaching. So whenever an index missing minus sign, there's a requirement, law of requirement. This is law of requirement. It has to be there. Okay. Okay. So there is no obvious symmetries that, but let me indicate it. What happens? Suppose you have start with a, okay. Just indicate that what if happen if you have start with a Lagrangian, which is not R, but contains, let's say, R square terms, a general Lagrangian. Same calculation will go through. What we will see, very interestingly, there will be some more extra terms. Apart from that, this piece will not only contains metric, but also contains curvature. Okay. That structure will come. Okay. But the symmetric structure in delta 1, delta 2 has to be same. Okay. So this is what we have, omega tilde for general relativity. Okay. And with this omega tilde, I will be able to calculate this omega. Okay. From the next class, we will look at these structures and define what is called the Noether current for field variations which are diffeomorphism. That means they are given generated by a vector field psi, infinitesimal diffuse, which are generated by a vector field psi. For those field configuration, we will calculate the conserved Noether current, which is conserved by equation of motion. We will construct the Noether charges for this and show how first law arises. That we will do without writing the Lagrangian. Then for Q, we will construct Q out of these omegas, okay, and actually show you that that gives you, with all these omegas taken into account, area by 4 as the black hole entropy. I think I will take 2 more classes to come to area by 4. Okay. Okay. So I'll stop here. In the tutorials, we will discuss the nature of this form omega. Okay. Okay. How does it closes? How to use equation of motion to put it close? What kind of equation of motion delta phi has to obey? What kind of equation of motion delta phi has to obey? Or whether phi is a solution of the equation of motion, what about delta phi? What are the solutions are? And you will see that you will require delta phi to solve the linearized equation of motion. That E, if you change delta E, that delta E has to be 0 to get this omegas to be a closed form. And that we will discuss in the tutorial section. I'll stop here. Please follow the derivation once again, okay? And if there is any index mistake, forgive me. Okay? Don't come to me. Index problem is yours. Okay. Thank you. Not in this. No. He does not write any explicit form. It is there in other places, I'm sure. Okay, is there any questions or any doubt? Or we can discuss later also. Thanks.